Let's look at an application of Stokes' theorem. In this particular problem, the vector field is xyz, comma y, comma z, and the surface in this case is the first octant portion of the cylinder z equal x squared over the circular disk, x squared plus y squared less than or equal to a squared. And so now, since we're in the first octant, as we project to the xy plane, that restricts the region to the first quadrant. And so now x would run from 0 to a, and the y would run from 0 to the square root of a squared minus x squared. Of course, this can simply be represented in terms of polar coordinates, where theta would run from 0 to pi over 2, and then of course r would run from 0 to a. So again, when you look at these types of surfaces, you always want to look at the aspects that can be clearly described to move the problem forward. Now again, we can see where Stokes' theorem is very valuable here. The line integral would be difficult, whereas the surface integral with Stokes' theorem would be something that we could execute. And so now, of course, we need the curl of f, so we have the nabla cross the vector field. So first let's do 2, 3. So in this case, 2, 3 would be 0. And then 3, 2, again, the z partial of y is 0. So we get 0 minus 0. And then 3, 1 will leave us with an xy. And then 1, 3 will leave us with a 0. So we have xy minus 0. And then 1, 2, the x partial of y being 0. And then 2, 1 will get a minus xz, as we have here. So the curl ends up 0 in the first coordinate, xy in the second coordinate, and negative xz in the third coordinate. So now, to finish off the components we need for Stokes' theorem, we need this particular component of the unit normal, and that's the negative zx, negative zy, and the 1. Of course, now this is easy to do. So the partial here with respect to x will be 2x, made negative is a negative 2x. The y partial is 0, and of course we have the 1, so that computation was simple. So now for the line integral, we will now replace that via Stokes' theorem through the surface integral of the curl of f. And so now we can go ahead and move to our region R, and we can substitute in this particular case the curl 0, comma xy, comma negative xz, dotted with our component of the unit normal, negative 2x, comma 0, comma 1. Now when we look at this particular computation here, the first two components of the dot product are 0, but the third one gives us a negative xz as we have here. And so now we can go ahead and replace z with its Cartesian equivalent, which is x squared. So this will give us the double integral over the region R of negative x cubed dA. So now, of course, we can factor the negative, and then we can go ahead and utilize our polar coordinate representation and replace x with r cosine theta, and that will give us a negative of the double integral r cubed cosine cubed theta, and then of course the Jacobian being r, so dA is replaced with r dr d theta. Now of course, let's go ahead and multiply by r, and that'll give us the negative of the double integral r to the fourth cosine cubed dr d theta. Like I said, again, the integrals are very straightforward with the polar coordinates. And so now, with respect to r, we just get add 1 divided by the new power. So we have the r to the fifth divided by 5. We have the negative of the integral from 0 to pi over 2 of cosine cubed theta. And then, of course, we just evaluate the r from 0 to a. The r being replaced with 0 zeroes this out, but the a here, replacing the r, will give us a negative a to the fifth over 5, which we can just place here. And then, of course, if you like, we can go ahead and integrate with respect to theta once we rewrite the cosine cubed. And of course, using our calculus 1, calculus 2, we can just write that as 1 minus sine squared theta times cosine theta. And that's ready to go. We can easily anti-differentiate cosine to get a sine. And then, of course, this is table ready because the derivative of sine is cosine. So, of course, when we anti-differentiate, we have the negative a to the fifth over 5. So we have a sine theta evaluated between 0 and pi over 2. And then, of course, here, add 1 divided by the new power. So that'll give us the cube of sine divided by 3 with the negative evaluated between 0 and pi over 2. And so now we notice that the lower limits give us 0, but the upper limits give us a sine theta of 1. So we'll have the negative a to the 5th divided by 5 times 1 minus 1/3. And then, of course, that gives us a 2/3 times the negative a to the 5th divided by 5, which gives us a negative 2a to the 5th divided by 15. So again, the computations here are usually made more executable when you utilize a coordinate system that is simple and straightforward. Often when we do long extended problems, we want our particular steps to be efficient. If you're doing a problem that only requires one technique, then you can be less efficient if you're trying to emphasize a particular theory. But when we're applying the divergence theorem, Green's theorem, or the more advanced version of Green's theorem, Stokes' theorem, we want our steps to be clean and efficient. So keep that in mind as you're doing these problems. And we are done.